The history of our planet is not written in ink or carved in words. It is written in stone. Every grain of sand, every fold of mountain, every ripple of shale beneath our feet is a page in an ancient book, one that has been written and rewritten for over 4.5 billion years. The Earth has no memory like ours. It doesn't dream or recall, but it records with patience, precision, and silence. Beneath the soil we walk upon lies an archive deeper than imagination. Layer by layer, sediment upon sediment, the planet has kept a record of its own becoming. Each stratum tells a fragment of the story, seas rising and retreating, continents drifting like ghostly rafts, volcanoes exhaling their molten breath, creatures being born, evolving, and fading into extinction. To the untrained eye, a cliff face is just a wall of rock, but to the geologist and the paleontologist, it is a cathedral of time. The faint bands of color, the subtle changes in texture, the buried fossils cut between the layers, these are senses and symbols in a language older than any spoken by human tongue. In these layers, time itself becomes tangible. One can trace the years not by the ticking of clocks but by the shift in fossils, by the sudden absence of one form of life, and the quiet emergence of another. And somewhere, hidden within this vast archive, there are lines thin, fragile, and yet unmistakable, that mark the boundaries between worlds. These are the great transitions, the dividing lines where life was reset, reshaped, or erased. There are few of these boundaries, and each one marks a cataclysm. One such line lies buried in rock strata across the globe, a ghostly band of clay, no thicker than a finger, yet powerful enough to tell of one of the darkest days in Earth's history. It marks the death of an era, the end of the dinosaurs, and the beginning of something new. Scientists call it the Cretaceous-Paleogene boundary, or the KPG boundary. For millions of years before that line was written, the Earth was alive with giants. Forests of towering conifers whispered under skies patrolled by pterosaurs. The land shook beneath the steps of creatures whose names echo through our childhoods: Tyrannosaurus, Triceratops, Ankylosaurus, Mosasaurus, a living pageantry of impossible scale and strength. But all of it, every war, every feather, every beat of those enormous hearts, ended in an instant. The rocks recorded. They hold the silence that followed. Above that thin boundary, the fossils change. The bones shrink. The world that follows is quieter, emptier, as if the planet itself had paused to catch its breath. In layers older than the boundary, life is abundant: tooth, claw, leaf, and bone. But above it, for thousands of years' worth of sediment, the record is almost bare. The great beasts vanish, replaced by the bones of small mammals no heavier than a cat, scurrying through a devastated world. No four-legged creature larger than 25 kilograms survived. 3/4 of all species were wiped away. It was as if Earth had taken a pen, drawn a final line, and begun a new chapter. The question, of course, is how? How does a thriving world end so suddenly? How can so much life vanish, leaving behind only dust and silence? That question remained unanswered for tens of millions of years, until a father and son, Walter and Luis Alvarez, cracked open a piece of limestone in Italy and found, hidden in the thinnest of layers, the fingerprint of a cosmic murder. But that is the next page in the story, the chapter of fire and sky, of impact and extinction, of how a rock from space ended the age of giants. In 1980, a quiet revelation shook the world of paleontology. Walter and Luis Alvarez, a father and son team, were examining rocks at the boundary between the Cretaceous and the Paleogene periods, the thin line that separates life before and after an extinction so vast it reshaped the planet. The rocks, ordinary in their appearance to anyone else, held something extraordinary, a whisper from the sky itself. Within the faint, dark line separating the age of giants from the era of the small and surviving, the Alvarezes discovered an element almost unknown on Earth: iridium, scarce in our planet's crust, yet abundant in meteorites. It was a clue, a message written across the continents, by forces beyond Earth. Here, in this fragile layer of rock, lay the evidence of a cataclysm of unimaginable scale. The Alvarezes proposed a theory that sounded almost impossible. An asteroid, an immense traveler from the dark reaches of space, had struck our planet 66 million years ago. 80 kilometers across, this cosmic projectile obliterated itself in the impact, leaving a scar on the Yucatan Peninsula in Mexico and scattering iridium around the world, a thin layer that would remain for eternity. The implications were staggering. Life on Earth had been thriving, growing in complexity and size. Dinosaurs ruled the land, sea, and sky. Mammals and birds had begun their cautious expansion. Forests swayed under the wind. Oceans teemed with monstrous creatures. And yet, in a moment of cosmic misfortune, that world ended. The impact unleashed forces that no living creature could withstand. Shockwaves traveled across the planet, toppling trees and triggering earthquakes of unimaginable magnitude. Fires raced across continents, igniting forests and releasing clouds of smoke that darkened the sky. Vast tsunamis rolled across oceans, erasing coastal life with a sweep of water more powerful than any storm. And then came the long night. For years, perhaps decades, the sun was obscured by dust and debris. The temperature plunged, disrupting climates and starving ecosystems. Plants withered, herbivores perished, and the predators that depended on them vanished in turn. The world became quiet in a way that would have been alien to the roaring Cretaceous, a silence heavy with the absence of giants. It is impossible to imagine the scale of this extinction in human terms. We think of storms, fires, and floods. We think of loss. But here, 3/4 of all species disappeared. Dinosaurs, once rulers of the earth, were gone forever. Sharks, ammonites, and many marine species vanished from the oceans. Insects, plants, and even the tiniest life forms were changed forever. And yet, from this devastation, life endured. Small mammals survived, scurrying in burrows and hiding from predators. Birds and insects persisted. Life, as fragile as it was, clung on, ready to expand into the empty world left behind by giants. The rocks preserved this story, layer by layer. Above the thin, iridium-rich boundary, fossils shrink. The bones of enormous creatures vanish, replaced by the tiny skeletons of survivors. And there in that quiet record is a lesson written across millions of years. Life is resilient, but it is also vulnerable. Catastrophe is always possible, and yet the earth endures. The KPG boundary is not just a mark of death. It is a hinge in the story of life, a pivot that led to mammals thriving, to birds taking to the sky, to ecosystems reshaping themselves in ways that would eventually allow humans to exist. It is a line in the stone where the past ended and the future began. Even now we can stand on the cliffs, in the deserts or on the coasts where this boundary lies exposed, and feel the echo of that cataclysm. The rocks speak in silence, whispering tales of asteroid fire, tsunamis, and darkness, and yet also of survival, resilience, and rebirth. And so, the stage was set for the next great drama. Long before humans existed, long before the dinosaurs even roamed Earth, had already endured deeper, darker crises, events that would change the very chemistry of the oceans, the air, and life itself. To understand those, we must travel further back, hundreds of millions, even billions of years, to a time when life itself faced its first great challenge. While the asteroid that ended the reign of dinosaurs was dramatic and immediate, it was not the most devastating extinction the planet had ever known. Nearly 200 million years earlier, Earth faced a calamity on a scale that defies imagination. An event so catastrophic it became known as the Great Dying. At the close of the Permian period, the planet's biodiversity collapsed almost entirely, wiping away life in an incomprehensible geological heartbeat. Unlike the KPG extinction, this devastation had no cosmic perpetrator. No asteroid fell from the sky, no sudden impact instantaneously erased ecosystems. Instead, Earth itself unleashed fury upon its inhabitants. The ground shook as massive volcanic eruptions began to spew rivers of molten rock, clouds of choking ash, and thick plumes of poisonous gases into the atmosphere. These eruptions were not localized. They occurred in vast regions, known as the Siberian Traps, covering millions of square kilometers. The planet's climate became unrecognizable. Oceans warmed, and then suffocated with low oxygen. Air thickened with carbon dioxide, turning skies into a choking haze. Acid rains fell upon forests and plains, corroding the land and poisoning freshwater sources. Species that had thrived for millions of years suddenly found themselves in an uninhabitable world. Life fell, not as a whisper, but as a roar of annihilation. Trilobites, ammonites, and the earliest land-dwelling reptiles and mammals were driven to extinction. Entire families of plants and marine creatures disappeared forever. It is estimated that 96% of marine species and 70% of terrestrial vertebrates were lost. The seas, once teeming with life, became deserts. Forests, once green and sprawling, turned to ashes. Even the smallest microorganisms, the foundation of the food chain, were swept away in this tide of death. The Great Dying reshaped the Earth in ways that would last for millions of years. Life did not simply bounce back. It had to start over in a world profoundly altered. Those species that survived were few, hardy, and adaptable. Evolution was forced to take a new path, one guided not by gradual change but by survival against extremes. In the aftermath, the Earth was quiet again, a silence etched into rock layers worldwide. Paleontologists can trace these layers today, sequences of sediment, lava, and ash that record the fiery destruction and the slow, uneven recovery that followed. The geological record is a testament to Earth's raw power, a reminder that the planet itself can become a destructive force capable of reshaping life on a global scale. This extinction, far deeper in time than the KPG event, foreshadowed a recurring theme in Earth's history. Life is resilient, but the planet is indifferent. The stage of existence has always been set not just by evolution and adaptation, but by fire, ice, and chemical upheaval. And long before these massive reptiles walked the Earth, before volcanoes sculpted continents, before oceans teemed with complex life, there existed a world of simpler beings, a world of microbes that thrived quietly in the shadows of hydrothermal vents. It was a world unprepared for the revolution that was to come, the birth of oxygen, the innovation that would eventually reshape the chemistry of oceans, skies, and life itself. The story of that first chemical upheaval, billions of years ago, is where the true roots of catastrophe lie. It is a tale that begins not with fire or impact, but with the quiet, invisible work of life itself. Microbes, small beyond imagining, were about to change the Earth forever, and in doing so, they almost destroyed themselves and all that depended on them. Long before the Earth had continents, forests, or even complex animals, it was a place of quiet, shadowed oceans and microbial life. At least 2.5 billion years ago, in what scientists call the Archean, the planet was a dark, watery world alive only with the smallest forms of life. These early microbes clustered around hydrothermal vents on the ocean floor, thriving in the chemical warmth and mineral-rich waters that bubbled from the Earth's crust. In this world, life was simple but astonishingly clever. The microbes had no need for light or oxygen. Their metabolisms fed on the minerals and gases released by the vents, hydrogen, sulfur compounds, and other elements that poured from the Earth's interior. In this confined environment, life flourished in microcosms, tight-knit communities bound by chemistry rather than sight or movement. Yet even in this constrained existence, change was inevitable. Mutations and genetic exchange allowed microbes to experiment with new ways of living. They swapped small pieces of genetic information in a quiet dance of evolution, creating new metabolisms and unlocking capabilities their ancestors had never imagined. In this slow, patient process, life became more diverse, more adaptable. From this innovation emerged a remarkable development: pigments. These tiny molecular tools allowed microbes to capture light energy from the sun, a resource previously untapped in these shadowy seas. Suddenly, the microbes could harness a new form of power, drawing energy directly from sunlight. The first steps toward photosynthesis had begun. But the first light-harnessing microbes were not like the green plants we know today. They were purple bacteria, strange and exotic, feeding on infrared light beyond the visible spectrum. Their chemistry was noxious and unusual. Hydrogen and dissolved sulfides were transformed into solid yellow sulfur and corrosive sulfuric acid. The shallow waters where these microbes thrived became a strange, stinking, toxic environment, a byproduct of their own ingenuity. And yet, this was only the beginning. Over millions of years, microbes continued to innovate. They developed green pigments, more efficient at capturing sunlight, and a simpler chemistry that relied not on sulfur but on water. Using carbon dioxide and water, these organisms produced energy to power their metabolisms, the foundation for the oxygen-producing photosynthesis that green plants and algae use today. But with this innovation came a deadly side effect: oxygen. To life in the Archean, oxygen was a new and dangerous element, a poison that could destroy the delicate molecular machinery of the microbes themselves. The world was unprepared for this byproduct of success. Where oxygen spread, it reacted violently with the chemistry of the oceans, with minerals, metals, and other molecules, creating a slow, creeping crisis that would soon escalate. In these early seas, life was on the cusp of a revolution that would transform the planet. Microbes, small and hidden in the darkness, had set in motion processes that would change the oceans, the air, and eventually every living thing on Earth. And yet, their innovation would also bring death on a scale that no asteroid or volcano could match, a mass extinction wrought not from without, but from the inside, from the very chemistry of life itself. The Archean world, bathed in strange light and filled with microbial communities, was a stage set for one of the Earth's most profound transformations, the Great Oxygen Catastrophe. And as oxygen began to spread, it would sweep across the oceans like an invisible tide, killing many of the life forms that had existed for billions of years, reshaping the biosphere in ways both terrifying and irreversible. In the quiet, shadowed oceans of the Archean, life was about to undergo a transformation that would echo through billions of years. The small, clustered microbes that clung to hydrothermal vents had discovered a new power: the ability to harness sunlight. This innovation, the earliest form of photosynthesis, allowed organisms to convert light into energy, opening a door to an entirely new way of life. But the first experiments with photosynthesis were far from gentle. The microbes that first absorbed sunlight were not green plants as we know them today, but purple bacteria, mysterious organisms thriving in infrared light. Their chemistry was strange and noxious, a delicate balance of survival and destruction. Using hydrogen and dissolved sulfides from the surrounding water, they produced energy, but at a cost. Solid yellow sulfur and corrosive sulfuric acid accumulated as byproducts. The shallow waters where these organisms lived became toxic, a stinking, acidic environment created by their own metabolic success. Yet even in this harsh world, evolution pressed onward. Through millions of years of mutation and genetic exchange, the microbial handshake that allowed them to share skills and innovations, new forms of photosynthesis emerged. Green pigments evolved, more efficient at capturing sunlight, absorbing red and blue wavelengths. The microbes discovered a simpler, cleaner chemistry. Instead of relying on sulfur, they could use ones that lacked the adaptations to survive in this new, oxygenated environment. Life was thriving, yet simultaneously, life was dying. This early oxygen revolution set the stage for a cycle of boom and bust that would continue for millions of years. Microbial populations would grow, saturate the shallow oceans with oxygen, and then collapse under the toxicity of their own waste. Oxygen levels would rise and fall in pulses, creating dramatic shifts in the chemical environment and leaving traces in the geological record. These cycles are preserved today in banded iron formations BIFs, the crimson and black layers of iron-rich rock that tell a story of life, death, and chemical transformation. The birth of photosynthesis was not merely a step forward in evolution. It was also the first act in a planetary-scale catastrophe. Life itself had changed the world, and in doing so, had triggered an extinction event that would reshape the biosphere. Oxygen, essential to most modern life, was first a poison, killing countless microbial communities and leaving only the adaptable survivors to inherit a transformed Earth. In these early oceans, under alien skies, and through billions of years of trial and error, the stage was set for the Great Oxygen Catastrophe, an event that would alter the chemistry of the oceans and the atmosphere, trigger mass extinctions, and pave the way for the rise of complex life. What began as a quiet innovation in the shadows of hydrothermal vents was becoming a force capable of remaking the planet. As the first oxygen-producing microbes flourished, their chemical innovations began leaving marks that would last billions of years. One of the clearest records of this ancient transformation can be found in the banded iron formations, or BIFs. These striking layers of rock, alternating in vivid red and deep black, are not just minerals, they are the story of a planet in upheaval, written in stone. The origins of BIFs were first glimpsed in the 19th century, when geologist William Burt, exploring northern Michigan in search of metal ores, discovered unusual rocks that made his compass behave strangely. Upon closer investigation, Burt found layers of iron-rich rock arranged in smooth, alternating bands, some just millimeters thick, others towering over a person. These rocks contained more than 30% iron, compared to the typical 5% in the Earth's crust. The IFs were more than geological curiosities. They were evidence of the dramatic chemical changes taking place in the oceans billions of years ago. In the Proterozoic oceans, about 2.4 billion years ago, photosynthetic microbes were pumping out oxygen into waters that had never before contained significant amounts of this reactive gas. Oxygen is extremely eager to combine with other elements, and in the ancient oceans, it found an abundant partner, dissolved iron. The iron, suspended in the water as green iron hydroxide, reacted with oxygen to form iron oxide, or rust. This reaction turned coastal and shallow waters a vivid, apocalyptic red, a warning sign of the chemical revolution unfolding beneath the surface. The red layers of the BIFs tell the story of oxygen interacting with iron over millions of years. When oxygen production exceeded the capacity of iron to absorb it, the toxic gas began accumulating in the oceans, suffocating microbial communities that had not evolved resistance. The black layers, often composed of silica-rich shales, represent periods when oxygen levels dropped and iron precipitation slowed, giving life a brief reprieve. This cycle of boom and bust, oxygen rising, iron rusting, life dying, recovery, repeated over hundreds of millions of years, creating the beautifully banded formations we see today. These geological formations are more than just ancient rocks. They are the Earth's diary of its first great chemical crisis. They capture the tension between life and the environment, a dance of survival and destruction that set the stage for every major shift in the biosphere to come. Each layer of iron oxide is a pulse, a heartbeat of a world in transition, marking moments when life both triumphed and nearly perished under the weight of its own success. But the story of the BIFs is not just about microbial life or chemical reactions. It is also a story of planetary change. As oxygen accumulated in the oceans, it began to fill every corner, reaching depths that had remained anoxic for billions of years. The reactive gas swept across the globe, poisoning microbes that clung to hydrothermal vents in the dark, killing communities that had survived unchanged for millions of years. Oxygen oxidized vital minerals, iron, sulfur, manganese, locking them away in forms inaccessible to primitive life, starving them of the very chemistry they relied upon. In this way, the BIFs record not only the rise of oxygen, but also the slow-motion extinction of archean life. They are a visible testament to the fact that life itself can reshape the planet, and in doing so, bring disaster upon its creators. The oceans were no longer merely a habitat. They became a chemical battlefield, where survival required adaptation or extinction. Through these red and black layers, we can imagine the ancient Earth, a world where shallow seas glowed crimson with the chemical energy of life, black depths hid fragile communities in darkness, and oxygen spread silently but lethally across the globe. The banded iron formations are a memory of this immense struggle, a reminder that even the smallest life forms can wield power over the entire planet. The BIFs mark a turning point, a prelude to the Great Oxygen Catastrophe, when oxygen would no longer be confined to the shallows. It would eventually saturate the oceans, seep into the atmosphere, and trigger consequences that reshaped the climate, the chemistry of the Earth, and the trajectory of life itself. In the early Proterozoic oceans, life and chemistry engaged in a slow, patient dance, marked by cycles of growth, collapse, and rebirth. This was the boom and bust cycle of early oxygen, a rhythm that would continue for millions of years and leave its mark on the geological record. As the first oxygen-producing microbes flourished in the sunlit shallows, they began to release oxygen faster than the oceans could absorb it. Initially, dissolved iron acted as a sponge, binding with the free oxygen to create iron oxide. The red layers of banded iron formations grew thicker as oxygen reacted with iron in the water column, sinking to the ocean floor as sediment. This was the boom phase. Oxygen levels were rising, microbial populations thrived, and chemical reactions transformed the oceans into a vivid, rust-colored landscape. But this success carried a hidden peril. The microbes that produced oxygen had not yet evolved resistance to their own waste product. As oxygen accumulated, it began to poison the very organisms that created it. The shallow water communities, crowded and vibrant, were suddenly overwhelmed. The chemical toxicity of oxygen disrupted delicate cellular processes, suffocating microbes in a silent but deadly tide. Life collapsed in what could be called the bust phase. Oxygen production slowed, microbial populations plummeted, and the red iron deposition temporarily halted. During these low oxygen periods, black layers of silica-rich shells and mudstones accumulated on the ocean floor, forming the alternating bands of the BIFs. These layers represent moments of respite, when life had a chance to recover and oxygen levels receded. The microbes that survived in pockets of safety, perhaps in slightly deeper waters or protected niches near the vents, slowly multiplied and evolved. Over time, this cycle repeated. Oxygen levels rose again as populations surged, only to crash under the chemical weight of their own success. Millions of years of this pulse created a rhythm in the oceans. Oxygen surged, microbial communities fell, sediments recorded the rise and fall, and then life began again. The BIFs are the stone diary of this repeated struggle, marking the planet's first great experiment with oxygen. This boom and bust cycle was not just a local phenomenon. It occurred globally, affecting nearly every ocean and shallow sea on the planet. As oxygen spread, it began to penetrate deeper waters, reaching communities of microbes that had never experienced it. Those life forms accustomed to dark, anoxic conditions could not survive. Oxygen reacted with minerals and chemicals essential to their survival, locking away iron, sulfur, and manganese, and depriving them of the resources they needed to live. These repeated cycles of abundance and death illustrate a powerful truth. Life can be both a creator and a destroyer. By producing oxygen, microbes reshaped the chemistry of the oceans and, in doing so, created conditions that nearly wiped themselves out. The Earth's first mass extinction, subtle yet immense, was already underway. Even in the midst of these catastrophic cycles, evolution pressed onward. Some microbes began to adapt, developing mechanisms to tolerate oxygen. These survivors would lay the foundation for a world in which oxygen was no longer a poison, but a life-giving element. Yet, during this era, the oceans were still a dangerous place. The interplay of oxygen, iron, and microbial life continued for hundreds of millions of years, creating a planetary-scale struggle invisible to the human eye, but recorded forever in the layers of rock that would one day be studied by geologists. Through these long, slow cycles, the Earth was transformed. Oxygen, once a deadly novelty, gradually became a permanent feature of the oceans. The BIFs captured this transformation in alternating bands of red and black, a testament to the power of life to shape the planet and to the cost of innovation when the consequences are greater than life itself can bear. As the boom and bust cycles of oxygen production continued, a slow but unstoppable transformation began. The oceans, once dark and anoxic, gradually filled with dissolved oxygen. This was the beginning of a global rusting, a planetary-scale chemical revolution that would permanently alter the Earth's effects were dramatic. Microbes that had never encountered oxygen, particularly those dwelling near hydrothermal vents in the deep ocean, were suddenly exposed to a hostile, oxidizing environment. They were poisoned, starved, and in many cases, entirely wiped out. Oxygen reacted with minerals such as iron, sulfur, and manganese, forming stable compounds and locking these essential elements away from the microbial communities that relied on them. Entire ecosystems fell silent, replaced by oceans chemically altered in ways that life had never experienced. Oceans and atmosphere. For hundreds of millions of years, the shallow seas had been arenas of intense chemical struggle. Photosynthetic microbes absorbed sunlight, produced oxygen, and thrived, only to be decimated by the very gas that sustained their growth. But over time, some organisms developed tolerance to oxygen, allowing their populations to expand and sustain oxygen production without immediate collapse. With fewer chemical buffers available, the oceans had become saturated with oxygen, and iron deposits were largely depleted. The gas could no longer be absorbed or neutralized as it once had. Oxygen began to accumulate in the ocean waters at unprecedented levels. The banded iron formations, those iconic red and black layered rocks, provide a visual record of this transformation. Each red layer marks a period when oxygen reacted with accumulate like a heartbeat, chronicling the repeated cycles of oxygen buildup, chemical depletion, and biological collapse. The global spread of oxygen was not a single, catastrophic event but a prolonged process, a slow suffocation and reinvention of life on Earth. Eventually, oxygen began to escape the oceans entirely, diffusing into the atmosphere. For the first time in Earth's history, the air above the planet contained a significant amount of oxygen. This seemingly subtle shift had profound consequences. Oxygen reacted with other atmospheric gases, including methane, one of the most potent greenhouse gases of the time. By breaking down methane into carbon dioxide, the atmosphere lost a vital heat-trapping blanket, dramatically reducing global temperatures. The planet's climate began to cool, setting the stage for an ice age that would engulf the Earth in frozen oceans and glaciers. In this way, the spread of oxygen was not only a chemical event but a climatic one. Life had changed the oceans and, by extension, the planet's atmosphere, altering the balance of energy and climate on a global scale. The innovation that had allowed photosynthetic microbes to thrive, the ability to harness the sun's energy through oxygen-producing photosynthesis, now posed a deadly threat to the majority of life on Earth. By studying the BIFs and other geologic evidence, scientists can trace the steady progression of oxygen from a local phenomenon in the shallow seas to a global presence that reshaped the planet. The oceans rusted, life was pushed to the brink, and Earth itself entered a new chemical era. This was the prelude to the Great Oxygen Catastrophe, a mass extinction that would eliminate nearly all life existing at the time and pave the way for oxygen-tolerant organisms to dominate in the eons to come. The global rusting reminds us that life is never separate from its environment. Even the smallest microbes can trigger planetary-scale transformations, and those transformations can, in turn, redefine the possibilities of life itself. Through oxygen, the planet experienced both creation and destruction, a chemical legacy that continues to shape Earth today. As oxygen gradually filled the oceans and began to escape into the atmosphere, the Earth entered a period of profound transformation, not just chemically, but climatically. For the first time, oxygen began interacting with other gases in the atmosphere, most notably methane, which at that time acted as a powerful greenhouse gas, trapping heat and keeping the planet warm. With rising oxygen levels, methane was broken down into carbon dioxide, a far less effective insulator. This sudden loss of heat-trapping methane caused global temperatures to plummet. The result was the Huronian glaciation, an ice age of unparalleled scale. Named for the glacial erratics, massive boulders transported and deposited by ice found on Lake Huron. This event transformed the planet into a snowball Earth, where ice sheets extended from the poles all the way to the equator. Continental shelves were buried under hundreds of meters of ice, and the shallow seas, once thriving with photosynthetic microbes, froze solid. For life that depended on sunlight, the opaque, ice-covered oceans were an inescapable death sentence. This ice age lasted for an extraordinary 300 million years, a time so vast that it can be difficult to imagine. During this frozen era, most ecosystems were silenced. Microbes that had survived the toxic oxygen waves now faced a new challenge: starvation and entombment in ice. Shallow coastal habitats, which had once supported microbial blooms, were locked beneath thick sheets of ice. Deeper waters remained dark and frigid, inhospitable to sun-dependent organisms. Even the most resilient microbial communities found themselves confined to rare pockets of liquid water, sheltered from both oxygen toxicity and ice entrapment. Yet, life is remarkably persistent. While the Huronian glaciation decimated global ecosystems, a small fraction of microbes endured in refuges untouched by extreme oxygen or ice. These survivors would serve as the ancestors for all subsequent life, carrying forward the legacy of oxygenic photosynthesis while adapting to a dramatically changed planet. The combination of rising oxygen levels and an extreme ice age represents one of the first examples in Earth's history of life reshaping the planet, and then having to survive the consequences of its own innovations. The Huronian glaciation also demonstrates the interconnectedness of Earth systems. Chemical changes in the oceans directly influenced atmospheric composition. In turn, these atmospheric shifts triggered massive climatic upheavals, proving that biology, chemistry, and climate are inseparable in the history of our planet. The photosynthetic microbes that once brought life-sustaining energy to the oceans had inadvertently triggered a global catastrophe, reshaping Earth's surface and climate for hundreds of millions of years. Though catastrophic, this ice age also set the stage for future evolutionary innovation. By eliminating the majority of existing microbial life, it created ecological opportunities for oxygen-tolerant organisms. These survivors, thriving in isolated niches, would eventually repopulate the oceans and continue to evolve increasingly complex metabolic and structural adaptations. Over geological timescales, these early adaptations laid the groundwork for the diversification of life that would follow in the Proterozoic and eventually in the Phanerozoic. In essence, the Huronian glaciation was both a punishment and a prelude. It punished life for altering the atmosphere with oxygen, yet it also prefigured a world in which oxygen would become a central feature of metabolism, ecosystems, and the eventual rise of multicellular organisms. The glaciers, ice sheets, and frigid oceans of this era were not just destructive. They were agents of selection, shaping the evolutionary path of life on Earth in ways that continue to echo billions of years later. The story of the Huronian glaciation reminds us that innovation can carry both promise and peril. The same processes that allow life to thrive can, over time, create conditions hostile to that very life. And yet, even in the harshest environments, life persists, adapts, and ultimately transforms the planet. While the Great Oxygen Catastrophe and the Huronian glaciation wrought unimaginable destruction across Earth's oceans and atmosphere, not all life was extinguished. Against staggering odds, a small fraction of microbial life found refuge in isolated niches, escaping the dual threats of toxic oxygen and an icy planet. These survivors would carry the genetic legacy that would eventually give rise to all life on Earth, connecting the ancient microbial world to the diversity we see today. The refuges for life during this period were remarkably specific. In the deep ocean, pockets of hydrothermal vent ecosystems remained insulated from oxygen-rich waters. Here, life continued to rely on the chemical energy emitted by the Earth itself rather than the sun. These vent communities, isolated from the global oxygenation, became safe havens, preserving microbial lineages that had enzymes capable of detoxifying oxygen, repairing cellular damage, and using it to extract energy more efficiently. In a cruel twist of fate, the very waste product that had nearly annihilated life became a cornerstone for future biological success. This period of survival and adaptation was not marked by grandeur or abundance. It was a slow, patient process in which life clung to whatever small, habitable corners of the planet remained. Yet these survivors set the stage for the eventual rise of complex ecosystems. The organisms that endured were not just passive remnants. They were pioneers of a new world, carrying with them innovations that would eventually allow life to flourish in oxygen-rich environments, ultimately leading to multicellular life and the eventual colonization of land. Studying these ancient survivors provides a window into resilience and persistence. Fossil evidence is scarce due to the microscopic size of these early microbes, but chemical signatures, isotopic data, and traces in banded iron formations reveal the dramatic story of survival. These traces show that while 99% of life was lost, the remaining 1% possessed a profound significance. They were the ancestors of every living organism that would follow. The lessons of this time are both humbling and inspiring. Life endured not because it was strong in the conventional sense, but because it was adaptable. It survived through isolation, patience, and biochemical innovation, proving that even in the face of planetary-scale catastrophe, persistence and flexibility can ensure continuity. The survivors of the Great Oxygen Extinction were the quiet heroes of Earth's early history, demonstrating that life is not merely a product of favorable conditions, but a force capable of enduring and shaping even the harshest realities. As oxygen continued to accumulate in the oceans and atmosphere, these resilient microbes would eventually expand, recolonizing areas previously inhospitable and setting the stage for an oxygenated world that could support larger, more complex life forms. The survival of these organisms illustrates the paradox of oxygen. A molecule that nearly destroyed the biosphere became essential for the evolution of complexity and diversity in the eons to follow. In reflecting on this period, we see that Earth's history is not a simple story of linear progress. It is a tale of catastrophe and survival, of destruction and innovation, of life constantly negotiating the delicate balance between chemical change, environmental stress, and evolutionary potential. The survivors of the Great Oxygen Catastrophe remind us that resilience in the face of adversity is the defining feature of life, a lesson that resonates not only in the past but across the entire trajectory of Earth's biological history. Following the devastation of the Great Oxygen Catastrophe and the prolonged chill of the Huronian glaciation, the Earth slowly began to stabilize. The survivors of these cataclysmic events, resilient microbes that had endured both toxic oxygen levels and encroaching ice began to flourish once again. Over millions of years, these oxygen-tolerant organisms expanded from isolated refuges, recolonizing the oceans and gradually transforming the planet into an environment capable of sustaining increasingly complex life. The key to this expansion was adaptation. Life had learned to cope with oxygen, the very molecule that had once threatened its existence. Microbes evolved sophisticated enzymes, such as superoxide dismutase and catalase, which neutralized the destructive effects of reactive oxygen species. This allowed cells to harness oxygen's energetic potential while minimizing its harm. By turning a once lethal byproduct into a powerful tool for energy production, life gained access to a far more efficient form of metabolism, setting the stage for biological innovation on an unprecedented scale. With the oceans now gradually saturated with oxygen, chemical gradients and nutrient cycles shifted dramatically. Previously toxic elements were now rendered inert or transformed into forms that could be incorporated into metabolism. Iron, once dissolved in vast quantities in the Proterozoic oceans, had largely precipitated into the iconic banded iron formations, leaving behind oceans with fewer chemical hazards for the survivors. Oxygen-tolerant microbes could now explore habitats previously off-limits, colonizing the shallow seas and coastal regions with newfound confidence. This expansion was gradual. For millions of years, microbial communities spread methodically, filling every niche they could find. These microbes were no longer just surviving. They were actively shaping their environment. Photosynthetic organisms continued to produce oxygen, further enriching the atmosphere and driving global changes in climate and chemistry. Each generation of microbes contributed to a positive feedback loop, increasing oxygen levels and making the planet progressively more habitable for aerobic life. The rise of oxygen-tolerant life also laid the groundwork for the evolution of more complex, multicellular organisms. With a stable supply of oxygen, energy-intensive processes, such as larger cell size, internal specialization, and eventual cooperative multicellularity became feasible. This was the first step toward the remarkable biological diversity that would later define the Earth, from algae to animals, and eventually to the rise of land-dwelling organisms hundreds of millions of years later. Even during this expansion, life remained fragile. Environmental pressures, nutrient availability, and lingering pockets of oxygen toxicity ensured that survival was never guaranteed. Yet, the ability of these organisms to persist, adapt, and proliferate in the face of such adversity exemplifies the incredible resilience and ingenuity inherent to life itself. The spread of oxygen-tolerant microbes marks a turning point in Earth's history, a moment when life shifted from mere survival in isolated refuges to an era of expansion and ecological dominance. This period, though distant in time, is critical for understanding the dynamics of life on Earth. It demonstrates that even after the most devastating catastrophes, life possesses an unparalleled capacity to adapt, innovate, and thrive, rewriting the rules of what is possible on a planetary scale. By gradually saturating the oceans and atmosphere with oxygen, these pioneering organisms created conditions that allowed the biosphere to stabilize, setting the stage for the later evolutionary leaps that would produce eukaryotes, multicellular life, and eventually the complex ecosystems that characterize our planet today. In essence, the survivors of the Great Oxygen Catastrophe were not just enduring life forms, they were architects of a new world, building the chemical and ecological foundations for everything that followed. After millions of years of boom and bust cycles, in which oxygen levels fluctuated violently and life struggled to survive, the planet slowly reached a point of chemical and ecological stabilization. The oceans, once dominated by toxic pockets of oxygen and chemical hazards, began to host a more consistent and balanced environment. This stabilization of oxygen levels marked a critical turning point in Earth's history, allowing life to expand not just in isolated refuges but across the broader marine landscape. As oxygen-tolerant microbes proliferated, they transformed the oceans from chemical battlegrounds into more habitable spaces. The continuous production of oxygen by photosynthetic organisms, combined with the depletion of reactive iron and other oxidizable elements, meant that the waters were now able to retain a higher, more consistent concentration of dissolved oxygen. This allowed more diverse microbial communities to develop, occupying a range of ecological niches and interacting in complex ways for the first time. Nutrient cycles also began to stabilize. With oxygen increasingly available, elements such as nitrogen and phosphorus became more mobile, supporting higher levels of biological productivity. Microbes that had previously been confined to chemical refuges could now venture into shallower waters, taking advantage of sunlight and dissolved nutrients to fuel their growth. This created the first widespread and relatively stable microbial ecosystems in the Proterozoic oceans. The stabilization of oxygen had profound implications for evolution. Microbes could now invest energy into growth, reproduction, and metabolic innovation rather than simply surviving the toxic effects of their own byproducts. The selective pressure shifted from mere survival to ecological competition and adaptation, driving an era of diversification. Organisms that could harness oxygen efficiently gained significant advantages, laying the foundation for more complex life forms in the future. During this period, microbial mats and early biofilms became increasingly common along continental shelves and shallow marine environments. These structures not only provided habitat for microbes, but also facilitated nutrient cycling and ecological interactions that were crucial for sustaining stable ecosystems. The interactions between oxygen-producing and oxygen-tolerant species created feedback loops that reinforced the presence of oxygen, gradually solidifying it as a permanent feature of the Earth's oceans and atmosphere. Importantly, this was not a rapid or instantaneous process. The transition to a truly oxygenated world occurred over tens of millions of years, a slow but steady shift that allowed life to adjust and adapt. Pockets of anoxic waters persisted in deeper ocean basins, serving as refuges for species still vulnerable to oxygen. These anoxic zones became evolutionary laboratories, where early life experimented with metabolic pathways that would eventually lead to the development of more sophisticated energy production strategies, including respiration. The ecological consequences of stabilized oxygen were far-reaching. Life could now exploit energy in new ways, supporting larger cell sizes, increased metabolic rates, and the gradual emergence of eukaryotic organism cells with nuclei and complex internal structures. This development marked the first step toward multicellularity, as organisms could afford to allocate energy to specialization, cooperation, and eventually, cellular differentiation. In effect, the stabilization of oxygen transformed the planet from a perilous, chemically hostile environment into one capable of supporting increasingly complex ecosystems. It allowed life to spread into new habitats, experiment with novel metabolic strategies, and lay the foundations for the explosion of biodiversity that would follow in the Proterozoic and eventually Phanerozoic eons. This period of relative stability was a quiet but crucial chapter in Earth's history. The catastrophic events of the Great Oxygen Extinction had decimated life, but the survivors' adaptations, combined with millions of years of ecological and chemical fine-tuning, created a world in which life could flourish once again. The oceans became not just a refuge but a cradle for innovation, preparing the stage for the emergence of eukaryotes, multicellular organisms, and the complex web of life that would ultimately dominate the planet. With the stabilization of oxygen in the oceans and atmosphere, life had reached a pivotal turning point. For billions of years, organisms had been simple, mostly single-celled microbes confined to specific chemical niches. Now, with oxygen abundant, and chemical hazards reduced, the stage was set for a dramatic leap in complexity. This leap took the form of the first eukaryotic cells, organisms with nuclei, internal membranes, and the capacity for far greater metabolic efficiency than their prokaryotic ancestors. The rise of eukaryotes was facilitated by oxygen itself. By enabling aerobic respiration, oxygen allowed cells to extract significantly more energy from organic molecules than the earlier anaerobic processes. With this surplus of energy, cells could support larger sizes, maintain internal structures, and develop specialized compartments, organelles, for distinct functions. This internal organization was revolutionary, permitting unprecedented cellular sophistication and laying the foundation for multicellular life. One of the key milestones in eukaryotic evolution was endosymbiosis, a process in which one cell engulfed another, forming a symbiotic relationship that became permanent. The most famous example is the origin of mitochondria, the energy powerhouses of eukaryotic cells. These ancient engulfed bacteria were themselves adept at using oxygen to produce energy, and by integrating them into a host cell, early eukaryotes gained a remarkable energy advantage. Later, a similar process would give rise to chloroplasts in photosynthetic eukaryotes, allowing the harnessing of sunlight directly within the cell. Eukaryotic cells were not just more efficient, they were also more versatile. Their larger size allowed for complex internal architecture, while their ability to compartmentalize functions meant that biochemical processes could occur simultaneously without interference. These advantages led to the development of diverse ecological strategies, from predators and symbionts to organisms capable of forming colonies. Over millions of years, eukaryotes diversified into an array of forms, exploring ecological niches that had previously been inaccessible to simpler life. The emergence of eukaryotes also had profound ecological consequences. By increasing the efficiency of energy use and nutrient cycling, these organisms contributed to greater productivity in oxygen-rich waters. Larger cells and more complex metabolic pathways allowed for new interactions between species, including predation, competition, and cooperation. These interactions created a dynamic and interconnected ecosystem, fostering further evolutionary innovation. At the same time, eukaryotes were still dependent on the lingering chemical and environmental conditions established by their microbial predecessors. Anoxic deep-sea refuges continued to exist, preserving pockets of ancient microbial diversity and maintaining chemical gradients that shaped evolutionary pressures. The interplay between oxygen-rich surface waters and low-oxygen deep waters created a layered biosphere, where different strategies for survival could coexist and experiment with new adaptations. This period of eukaryotic expansion marked the beginning of a slow but steady march toward multicellularity. As single-celled organisms specialized and cooperated, they formed colonies capable of division of labor, the first hints of tissues and organs. Oxygen not only supported more energy-intensive processes, but also made it possible for cells to survive in larger, more complex arrangements, paving the way for life to evolve beyond the microscopic scale. By the end of this phase, Earth's oceans had transformed into a thriving, oxygenated ecosystem teeming with eukaryotic innovation. Life was no longer constrained to isolated, chemically marginal habitats. It had begun to dominate the sunlit seas, experimenting with complexity, cooperation, and competition. These evolutionary experiments would eventually lead to the emergence of multicellular organisms, laying the foundation for the incredible diversity of life that would follow hundreds of millions of years later. The rise of eukaryotes was more than a biological milestone, it was a planetary transformation. Oxygen-tolerant survivors of earlier catastrophes had set the stage, creating a chemically stable, energetically rich environment in which complexity could flourish. What began as tiny, single-celled pioneers would eventually lead to the wide array of life forms that populate the Earth today, from algae and fungi to the ancestors of all animals. With eukaryotic cells thriving in oxygen-rich oceans, life began to explore new strategies for survival. One of the most significant evolutionary innovations during this time was the transition from single-celled life to multicellularity. This shift allowed organisms to grow larger, specialized cells for different functions, and interact with their environment in increasingly sophisticated ways. Multicellularity began with simple colonies of eukaryotic cells. These early colonies were loose aggregations of cells that stuck together after division. While each cell retained the ability to survive independently, being part of a collective offered distinct advantages. Cells could share resources, protect one another from environmental stress, and coordinate responses to changes in their surroundings. Over time, natural selection favored colonies with increased cooperation, tighter cell adhesion, and division of labor, setting the stage for true multicellular life. One of the key drivers of multicellularity was the availability of oxygen. Aerobic respiration provided enough energy to support larger cell sizes and more complex structures, which single-celled organisms alone could not sustain. Cells could afford to specialize. Some focused on nutrient acquisition, others on defense, and still others on reproduction. This specialization allowed multicellular organisms to exploit ecological niches inaccessible to solitary microbes, from shallow sunlit waters to deeper, oxygenated zones. Multicellularity also opened the door to structural innovation. Cells in colonies could arrange themselves into sheets, filaments, or clusters, creating rudimentary body plans. These early arrangements allowed organisms to move more efficiently, capture sunlight for photosynthesis, or filter nutrients from the water. Gradually, these primitive body plans became more sophisticated, giving rise to diverse forms of multicellular life that could survive in a variety of aquatic environments. The evolutionary benefits of cooperation were immense. By pooling resources, multicellular organisms could withstand environmental stresses that would have destroyed single cells. Colonies could better resist predation, compete for space, and recover from chemical or climatic disruptions. In essence, multicellularity amplified the survival advantages conferred by oxygen-rich environments, allowing life to become more resilient and versatile. Genetic innovation supported this transition. Eukaryotic cells could communicate and coordinate through chemical signals, laying the groundwork for developmental processes. Mutations that promoted adhesion signaling and differentiation were selected for, gradually leading to increasingly complex multicellular forms. Over millions of years, these incremental changes produced organisms capable of performing coordinated functions, an essential step toward the evolution of tissues and organs. Environmental conditions continued to shape multicellular evolution. Oxygen gradients in the ocean, availability of nutrients, and fluctuations in light all imposed selective pressures that guided the adaptation of early multicellular organisms. Some colonies thrived in sunlit shallows, optimizing photosynthesis, while others specialized for survival in slightly deeper waters, developing mechanisms to capture scarce nutrients. This diversification established the foundation for the complex ecosystems that would later dominate Earth's oceans. By the end of this period, the planet had entered a new chapter. Life had moved beyond simple, single-celled forms, exploring cooperation, specialization, and larger body plans. These early multicellular organisms were still small and largely microscopic, but their emergence was a monumental step toward the incredible diversity of life that would eventually populate the seas, the land, and the air. In summary, the rise of multicellularity was a story of collaboration, innovation, and resilience. The energy provided by oxygen, the organizational capabilities of eukaryotic cells, and the selective pressures of the environment combined to enable life to reach beyond its single-celled origins. These first multicellular organisms were pioneers, laying the groundwork for complex ecosystems and paving the way for the evolutionary revolutions yet to come. As multicellular organisms began to emerge, the planet itself was undergoing profound transformations. Oxygen, once a deadly waste product, had now become a vital force shaping life and the environment. The accumulation of oxygen in oceans and atmosphere created a feedback loop where life altered its surroundings, and those altered surroundings, in turn, guided the course of evolution. The first effect of rising oxygen levels was chemical and ecological. Oxygen readily reacts with minerals and gases, transforming the very composition of the oceans. Iron, sulfur, and other reactive elements that had dominated earlier oceans were gradually oxidized, forming deposits that are preserved today in banded iron formations. These chemical changes stabilized the environment, making it more hospitable for the growth of complex life. Nutrient cycles became more efficient, allowing multicellular organisms to access the building blocks of life more reliably. With oxygen abundant, ecosystems became increasingly layered. In the sunlit shallows, photosynthetic organisms flourished, forming dense microbial mats and early colonies of multicellular life. These communities produced oxygen continuously, reinforcing the chemical transformation of their environment. Below, in deeper waters, anaerobic microbes persisted in oxygen-deprived refuges, maintaining pockets of older, simpler life forms. This vertical stratification of ecosystems created a dynamic interplay between oxygen-rich and oxygen-poor zones, driving evolutionary experimentation and diversification. The rise of oxygen also influenced the evolution of metabolism. Aerobic respiration, far more efficient than anaerobic processes, allowed organisms to extract greater energy from the same nutrients. This surplus energy supported larger body sizes, faster growth, and more sophisticated cellular structures. Cells could now maintain internal compartments, specialize functions, and support communication with other cells, setting the stage for more complex multicellular organisms. As these ecosystems expanded, life began to shape the physical environment, creating a self-reinforcing cycle of ecological transformation. Life and environment became intertwined, evolving together over millions of years. Predation and competition also emerged as ecological forces. With multicellularity came the ability to consume other organisms effectively. Early predators may have fed on smaller cells or simple colonies, while prey evolved strategies to survive, such as protective layers, adhesion to surfaces, or chemical defenses. This early arms race further accelerated evolutionary innovation, increasing diversity and complexity in the oceans. By the end of this period, Earth's first ecosystems had become remarkably intricate. Oxygen had transformed from a deadly byproduct into a life-enabling force. Multicellular life had begun to explore cooperation, specialization, and predation, creating feedback loops that shaped the physical and chemical environment. Nutrient cycles, sedimentary patterns, and oxygen levels were all influenced by living organisms, setting the stage for the next wave of evolutionary advances. In essence, the interplay between oxygen and multicellular life during this era was a story of cause and effect, of life shaping the planet and the planet shaping life. It demonstrated that biology and geology are inseparable partners, each driving the other in a complex dance that would continue for billions of years, ultimately leading to the diverse and interconnected ecosystems we observe on Earth today. With multicellular organisms becoming increasingly common, Earth's oceans entered a new era of biological interaction. Life was no longer confined to passive existence. The emergence of larger, mobile, and specialized organisms introduced predation and competition as driving forces in early ecosystems. These dynamics fostered evolutionary innovation and set the stage for the complex food webs that would define Earth's biosphere for billions of years to come. Predation marked a profound shift in life strategies. Some of the earliest multicellular organisms evolved mechanisms to feed on smaller cells or simple colonies. Even a tiny predatory organism could gain a significant advantage, consuming nutrients directly rather than relying solely on photosynthesis or diffusion from the surrounding environment. In turn, prey organisms faced selective pressures to survive, leading to the evolution of defensive adaptations. Protective outer layers, increased mobility, and chemical deterrents emerged as natural responses to predation. This constant interplay between predator and prey created an evolutionary arms race, driving complexity and diversity. In even the simplest of life forms, competition too became a significant force. As oxygen-rich ecosystems allowed more energy to be harnessed, organisms competed for sunlight, nutrients, and space. Photosynthetic organisms vied for positions in sunlit shallow waters, forming dense mats and colonies. Even small differences in size, shape, or metabolic efficiency could determine which organisms thrived and which were outcompeted. Over time, this pressure favored specialization and cooperation among cells, leading to more stable multicellular colonies and the first true ecological niches. The interactions of predation and competition led to the establishment of early food webs. Microbial mats and multicellular colonies became foundational producers, capturing sunlight and converting it into energy-rich compounds. Herbivorous or filter-feeding organisms consume these primary producers, while early predators fed on smaller multicellular life, creating layers of energy transfer within the ecosystem. Even in this primordial ocean, the principles of ecological organization, producers, consumers, and decomposers, were beginning to take shape. Mobility emerged as another critical adaptation. Organisms that could move, even slowly, gained access to new resources and avoided localized hazards. The evolution of primitive appendages, cilia, or flagella allowed organisms to explore their environment more effectively, escape predators, or position themselves optimally for sunlight capture. Movement also facilitated interactions among colonies, such as the exchange of genetic material or the coordination of group behaviors, enhancing survival in increasingly competitive ecosystems. Environmental variability further shaped early ecosystem complexity. Oxygen levels fluctuated, nutrient availability varied, and shallow marine habitats experienced changes in temperature and light penetration. Organisms that could tolerate or exploit these variations gained evolutionary advantages. Over time, these pressures produced an astonishing variety of life forms, each adapted to specific microenvironments. The oceans became a mosaic of habitats, each with its own ecological rules and survival strategies. Chemical communication also played a growing role in ecosystem dynamics. Early multicellular organisms could exchange signals to coordinate growth, movement, or defense. This form of proto-communication allowed colonies to respond collectively to threats, enhancing their survival. Over generations, such signaling mechanisms became more sophisticated, laying the groundwork for the intricate communication networks observed in modern organisms. By the end of this period, life had established a dynamic, interconnected web of interactions. Predation, competition, mobility, and chemical signaling combined to create ecosystems that were far more complex than anything seen in the microbial-dominated world that preceded them. Even in microscopic scales, these early ecosystems exhibited patterns of organization, resilience, and feedback that would define Earth's biological future. In summary, the emergence of predation and competition transformed life from passive survival into an interactive, adaptive force. Organisms not only adapted to their physical environment but also to each other, giving rise to the first complex ecosystems. These processes set the stage for later evolutionary milestones, including the rise of animals, the colonization of land, and the incredible diversity of life that we see today. As early multicellular life thrived in oxygen-rich oceans, a new set of evolutionary innovations began to emerge, structural adaptations that would forever change the landscape of life on Earth. These innovations, including skeletons, shells, and other hard parts, provided protection, support, and new ecological opportunities, setting the stage for one of the most remarkable events in Earth's history, the Cambrian explosion. The first major advantage of hard parts was defense. In a world increasingly shaped by predation, soft-bodied organisms were vulnerable. A predator could easily consume an unprotected colony or a fragile multicellular organism, reducing its chances of survival. The development of exoskeletons, shells, or mineralized plates allowed organisms to resist predation. Even simple coatings of calcium carbonate or silica provided a significant survival benefit, shielding vital tissues from attack. Over time, these structures became more elaborate and specialized, supporting a greater diversity of life forms. Hard parts also provided structural support. As organisms grew larger and more complex, soft tissues alone were insufficient to maintain shape and function. Skeletons and internal support structures allowed for increased body size, more complex movement, and enhanced feeding strategies. These structural innovations also enabled the development of appendages, such as spines, claws, or grasping limbs, giving organisms the ability to interact with their environment in new ways. Mobility, feeding, and reproductive strategies all benefited from the presence of durable structural components. The chemical environment of the oceans played a crucial role in enabling the formation of hard parts. Increased levels of calcium, magnesium, and silica, along with higher oxygen concentrations, allowed organisms to biomineralize efficiently. These minerals were readily available in shallow marine environments, making it possible for multiple lineages to evolve hard parts independently. This convergent evolution led to a rapid diversification of forms, with different species experimenting with a variety of protective and structural solutions. Hard parts also influenced ecosystem dynamics. Organisms with skeletons or shells could dominate specific ecological niches, competing more effectively for food and space. Their remains contributed to the formation of reefs, sandbanks, and other habitats, creating new microenvironments for other organisms to exploit. In this way, the rise of hard-bodied organisms not only transformed individual species, but reshaped entire ecosystems, laying the foundation for the complex communities of the Cambrian period. The evolutionary feedback was profound. As predators encountered more armored prey, they evolved stronger jaws, sharper appendages, and improved hunting strategies. This arms race between predators and prey accelerated evolutionary innovation, driving both defensive and offensive adaptations to unprecedented levels. The result was a rapid increase in morphological diversity, a prelude to the explosion of new life forms that would soon follow. Another consequence of hard parts was the fossil record itself. Soft-bodied organisms rarely leave behind traces, but skeletons, shells, and mineralized structures are far more likely to fossilize. This preservation allowed paleontologists to reconstruct early ecosystems with greater clarity, revealing the diversity and complexity of life before and during the Cambrian period. The development of hard parts thus not only shaped life at the time but also ensured that future generations could study the evolutionary story in detail. In summary, the rise of skeletons and hard parts marked a pivotal moment in Earth's evolutionary history. These innovations provided protection, structural support, and ecological advantage, setting the stage for the Cambrian explosion. Organisms were no longer entirely soft-bodied and vulnerable. They could now defend themselves, grow larger, and exploit new ecological niches. The evolutionary arms race intensified, ecosystems became more complex, and the foundations were laid for the incredible diversification of life that would soon transform the oceans and ultimately the planet. Following the rise of hard parts and skeletons, Earth entered one of the most transformative chapters in its biological history, the Cambrian explosion. Beginning around 541 million years ago, This remarkable period witnessed an unprecedented diversification of life, a rapid proliferation of complex organisms, and the establishment of nearly all major animal phyla that still exist today. The Cambrian explosion represents the moment when life truly began to explore its full potential, both in form and function. The oceans were the stage for this evolutionary drama. Shallow marine environments, rich in minerals and oxygen, provided ideal conditions for innovation. Organisms were no longer constrained to simple, soft-bodied forms. Instead, they began to experiment with size, shape, and specialization. Predation had already emerged, and its presence acted as a powerful evolutionary pressure, encouraging organisms to develop shells, spines, and other defenses. Mobility became increasingly sophisticated, allowing creatures to escape predators, search for food, and colonize new ecological niches. During this period, the pace of evolutionary innovation accelerated dramatically. Organisms evolved segmented bodies, jointed limbs, and sensory organs that allowed them to detect light, movement, and chemical signals. Eyes, though simple at first, provided a new means of perceiving the environment, and soon evolved into highly complex organs capable of detailed vision. These adaptations gave predators and prey primary producers, such as photosynthetic algae and cyanobacteria, supported herbivorous consumers, which in turn supported carnivorous predators. The interactions among these organisms created dynamic ecosystems, with competition, predation, and cooperation shaping evolutionary outcomes. Early reefs formed as sessile organisms, such as sponges and primitive corals, stabilized the seafloor, providing habitats for other species and increasing biodiversity. One of the most remarkable aspects of the Cambrian explosion was the emergence of bodied plants that would persist for hundreds of millions of years. Arthropods, mollusks, echinoderms, and chordates all made their first appearances, each developing unique structures and strategies for survival. This was an era of experimentation on a grand scale. Some lineages would survive and evolve into modern groups, while others would vanish, leaving only fossil traces as testimony to their brief existence. Environmental factors played a crucial role in enabling this explosion of life. Oxygen levels had stabilized at higher concentrations, allowing larger and more active organisms to thrive. Mineral-rich waters facilitated the development of skeletons and shells. Changes in ocean chemistry and the availability of calcium and other essential elements provided the building blocks for structural innovations. Together, these factors created the perfect conditions for life to diversify at an astonishing pace. The Cambrian explosion also set the stage for future evolutionary milestones. The establishment of complex food webs and ecological interactions created selective pressures that would continue to drive innovation. The diversification of sensory organs, appendages, and defensive structures laid the foundation for the evolution of more sophisticated behaviors, including burrowing, hunting, and even early forms of social interaction. Life was no longer passive. It had become dynamic, adaptive, and increasingly aware of its environment. From a paleontological perspective, the Cambrian explosion is invaluable. The abundance of hard parts and skeletons left behind a rich fossil record, providing scientists with detailed insight into early ecosystems, evolutionary trends, and the emergence of modern animal phyla. The fossils reveal the dramatic increase in size, complexity, and diversity that characterized this period, capturing a snapshot of life's most significant evolutionary leap. In summary, the Cambrian explosion was a turning point in Earth's history, marking the transition from simple, soft-bodied life forms to a vibrant, complex, and highly diverse biosphere. Predation, mobility, structural innovation, and environmental factors combined to create ecosystems of unprecedented intricacy. Nearly all major animal phyla emerged during this period, establishing the blueprint for future evolutionary developments and setting the stage for the rich tapestry of life that continues to evolve today. After the remarkable burst of life during the Cambrian explosion, Earth's oceans continued to teem with an ever-increasing diversity of organisms. The Ordovician period, beginning around 485 million years ago, saw marine ecosystems become more complex and interconnected. The seas were no longer just home to isolated, simple organisms. Instead, intricate food webs formed, linking primary producers, herbivores, and predators in a delicate balance that would shape the evolution of life for millions of years. During the Ordovician, invertebrates such as brachiopods, bryozoans, mollusks, and early cephalopods flourished. Reef-building organisms, including early corals and stromatoporoids, created structures that provided shelter and breeding grounds for countless smaller species. Predation pressures continued to escalate, prompting the evolution of thicker shells, spines, and other defensive adaptations. The ocean floor became a dynamic environment, with organisms burrowing into sediments, scavenging detritus, and establishing territories. One of the defining characteristics of this period was the continued expansion of biodiversity. The Ordovician radiation, sometimes called the Great Ordovician Biodiversification Event, saw an explosion in the number of species, families, and genera. Life was diversifying not just in form, but also in ecological role. Breezers, filter feeders, and predators developed increasingly specialized feeding strategies. These adaptations allowed ecosystems to become more resilient and dynamic, capable of sustaining a greater number of species in the same habitat. As marine life thrived, Earth's climate played an influential role. The Ordovician began with relatively warm seas and high sea levels, allowing shallow continental shelves to be flooded and colonized by diverse marine communities. However, toward the end of the period, the planet entered a brief but intense glaciation, causing sea levels to drop and dramatically altering marine habitats. This glaciation triggered one of the earliest known mass extinction events, reshaping ecosystems and eliminating many species that had thrived in the shallow seas. The Silurian period followed, beginning around 443 million years ago, and marked a time of recovery and further innovation. Coral stromatoporoid reefs expanded, forming complex three-dimensional habitats that supported a multitude of invertebrates and early jawless fish. The first jawed fishes appeared during this time, a development that would eventually lead to the dominance of vertebrates in marine ecosystems. The increasing mobility and predatory efficiency of these fish drove further ecological innovation, creating selective pressures that shaped the evolution of other species. The Devonian period, starting around 419 million years ago, is often called the Age of Fishes due to the remarkable diversity and abundance of fish species. Placoderms, early cartilaginous fishes, and lobe-finned fishes evolved a variety of adaptations for hunting, swimming, and interacting with their environments. These aquatic ecosystems became increasingly structured, with predators, herbivores, and scavengers occupying specialized niches, establishing complex trophic networks that resemble the ecosystems of modern seas. Perhaps the most revolutionary development of the Devonian was the initial colonization of land. Early plants, originating from simple, moss-like ancestors, began to spread across terrestrial environments, stabilizing soils and creating microhabitats that could support other life forms. Primitive vascular plants allowed for taller growth, improved nutrient transport, and the formation of the first forests. These early forests not only transformed landscapes, but also contributed to the atmospheric carbon dioxide cycle, influencing climate over geological timescales. The first terrestrial animals, small arthropods, such as millipedes and arachnids, began to explore these new habitats. The move onto land presented new challenges: gravity, desiccation, and temperature fluctuations, but also opportunities. Insects and other invertebrates could exploit untapped food sources and avoid aquatic predators. Over millions of years, These pioneering species laid the groundwork for the dramatic radiation of terrestrial life that would come in the Carboniferous period. By the end of the Devonian, marine ecosystems were dominated by diverse fish, reef-building organisms, and complex invertebrate communities, while the first steps on land had created the beginnings of terrestrial ecosystems. However, life on Earth was not yet finished with its trials. The late Devonian extinction events, occurring in pulses, would eliminate many marine species and reshape ecosystems once again, setting the stage for the next evolutionary chapter. In summary, the Ordovician to Devonian periods represent a time of unprecedented growth and experimentation in Earth's history. Marine ecosystems became increasingly complex. Predation and mobility drove evolutionary innovation, and the first plants and animals ventured onto land. These milestones set the foundation for future biodiversity, ecosystems, and the eventual rise of terrestrial life as a dominant force on the planet. Following the Devonian period, Earth entered the Carboniferous period, beginning around 359 million years ago, a time of lush landscapes, towering forests, and an extraordinary surge in biodiversity. The planet's continents were covered by dense swampy forests dominated by giant lycophytes, horsetails, and ferns. These forests transformed Earth's atmosphere, increasing oxygen levels to concentrations higher than those of today, while simultaneously sequestering vast amounts of carbon dioxide in the form of peat. Over millions of years, this peat would compress into the coal deposits that humans would eventually mine, powering the Industrial Revolution. The Carboniferous was also an era of extraordinary animal life. Arthropods grew to enormous sizes, likely due to the high oxygen levels, with dragonfly-like meganeuros sporting wingspans of over 70 centimeters and giant millepedus creeping through the forest floors. The seas teemed with diverse fish, early amphibians, and invertebrates, while the first seed-bearing plants, the gymnosperms, began to emerge, creating a bridge between primitive plants and the towering forests of later periods. It was during the Carboniferous that vertebrates began to establish a more permanent presence on land. Amphibians, which had first emerged in the Devonian, diversified into a multitude of forms, taking advantage of the moist environments created by the dense forests. However, the limitations of amphibians, tied to water for reproduction, prompted further innovation. Reptiles, which evolved from amphibian ancestors, developed adaptations that allowed them to reproduce entirely on land. The amniotic egg, with its protective shell and nutrient-rich yolk, enabled reptiles to venture far from water sources, opening vast new ecological niches and paving the way for the eventual rise of dinosaurs. As life flourished on land and in the seas, Earth's climate continued to fluctuate. During the late Carboniferous, extensive glaciations in the southern hemisphere led to periodic cooling, sea level fluctuations, and shifting habitats. These environmental changes prompted evolutionary experimentation, forcing organisms to adapt, migrate, or face extinction. Despite these challenges, life remained remarkably resilient, diversifying and exploring new forms, behaviors, and ecological roles. The subsequent Permian period, beginning around 299 million years ago, represented the final chapter of the Paleozoic era. Continents merged to form the supercontinent Pangaea, creating vast interior deserts and altering ocean circulation patterns. These changes led to dramatic shifts in climate, with extreme temperatures and fluctuating rainfall affecting both terrestrial and marine ecosystems. During the Permian, reptiles continued to diversify, giving rise to a wide range of forms, from small agile predators to massive herbivores. Amphibians persisted but were increasingly confined to wetter environments. In the oceans, the dominance of fish continued alongside corals, mollusks, and other invertebrates. Reef systems became more complex, and new predatory strategies emerged, heightening the evolutionary arms race that had driven diversification for hundreds of millions of years. However, The Permian period also set the stage for Earth's greatest mass extinction, the Permian-Triassic extinction, or the Great Dying. Environmental stresses accumulated over millions of years. Volcanic eruptions in what is now Siberia released enormous amounts of lava, carbon dioxide, and toxic gases into the atmosphere, disrupting climate and ocean chemistry. Oxygen levels fluctuated, temperatures soared, and acidification transformed marine habitats. Ecosystems, though resilient, reached a tipping point. The Great Dying would eliminate nearly 96% of all marine species and 70% of terrestrial vertebrates, making it the most catastrophic extinction in Earth's history. Reefs collapsed, amphibian diversity plummeted, and many early reptiles and synapsids disappeared. The extinction reshaped life on Earth, clearing ecological niches and setting the stage for the rise of new dominant groups, including archosaurs, the ancestors of dinosaurs, and crocodiles. In summary, the Carboniferous and Permian periods were times of incredible ecological experimentation and complexity. Towering forests transformed the atmosphere, insects and amphibians reached unprecedented sizes, and reptiles innovated new strategies to conquer terrestrial environments. Yet, this period also illustrates the fragility of life in the face of environmental upheaval. The evolutionary successes of these eras would ultimately meet with disaster during the Permian mass extinction, highlighting a recurring theme in Earth's history. Life is both resilient and vulnerable, constantly adapting to the ever-changing planet. And so, after billions of years of chaos and creation, destruction, and renewal, we've reached the end of our journey, the incredible story of how Earth became what it is today. From molten beginnings to frozen worlds, from the first sparks of life to the rise and fall of entire kingdoms of creatures, the story of our planet is one of endless transformation. Every grain of sand, every fossil, every mountain peak and ocean wave carries the memory of these ancient events, written quietly in stone. If you've made it this far, you've just listened to the entire history of the Earth from its fiery birth to the dawn of the modern world. Take a deep breath, let it all sink in, and remember how small yet extraordinary our place in this cosmic story truly is. Thank you so much for watching. If you enjoyed this journey through time, don't forget to like, subscribe, and leave a comment to tell us what you thought of this incredible story. It helps the channel grow and lets us know what kinds of journeys you'd like to explore next. Until then, rest easy, dream deeply, and we'll see you in the next video, where the story of the universe continues.